So the first panel is going to focus on something that remains, I think, one of the holy grail for wireless communication. That is, how do we build wireless systems we can bet our lives on? Right? These are those real-time, mission-critical systems for control and so on. Right? So we have a panel of leading experts from both industry, diverse industry, and academia. So what I do, this will be similar to yesterday. I think two of us are here in person, two online. We'll give them a chance to, because we would have a little bit time, so we'll give them up to about 10 minutes or so time to share their perspective for the field in general, and then we'll dive into the discussions. If folks in person don't mind, we'll start with online. So, Roger, do we have Mohammed, Dave? Hey, good morning, Dave and Mohammed. Yeah, thanks for joining us. I know it's very early for Dave. Thanks. So, well, how about we start with Mohammed? So Mohammed is a research scientist at the National Institute of Standard and Technology. They have a group that actually focuses on industrial wireless networks. Mohammed himself has been doing a lot of exciting work across modeling, design, validation, and so on. So, Mohammed, we'll give the floor to you. Do you want to share? If you have any slides,
so yeah, I have a slide. Should I share my video as well? I'm not sure what's the setting over there. Like,
so I think you can share your screen if you are on WebEx.
Okay. Can see it well?
Yes, we can see it now.
Okay, but yeah, do you want me to open my video or the screen?
We can see the screen, but somehow we don't see your video yet.
No, it's not on. That's what I'm asking. Should I turn it on? Like.
Yeah, we'd love to see you.
Okay. Okay.
If if that's appropriate, but yeah.
No, I'm at office, so I think that's okay. Fine. Okay, let me share my screen.
Yes.
Everything should be working now. Okay, hello, good morning, everyone. So I will first thank you for inviting me to this panel. I think that's really interesting, and thank you for being here. And thank you, Hongui, for the introduction. So I will give a quick introduction about what we are doing, who we are, and then hopefully later in the discussion we can talk in more details about this. So again, my name is Mohammed Kashif Hani. I'm a research scientist with the Industrial Wireless Systems team at NIST. I have been working with this team in the industrial wireless systems for like almost 8 years now. So let's see slides. So for those of you who are not very familiar with NIST, so NIST is really part of the federal government. It's part of the U.S. Department of Commerce. So practically, I would say we could have been invited to the second panel as well, but I would say our team really is more like a research team. So that's why we are like more relevant to this panel. NIST has been doing that work for a very long time, established in 1901, and we have a very large number of like employees in different fields, really. And we have our main headquarters, like our main campus in Gaithersburg, Maryland. So the general mission for NIST is really to promote the innovation and U.S. industrial competitiveness in measurement science, standards, and technology. And that really includes a wide area of aspects, but I would say the relevant areas is the scientific and engineering research that we are doing, and of course one part of it will be the wireless communication, and also have like leading a number of advanced manufacturing national programs, and of course one part will be the technology transfer and innovation, which we have been doing I would say very well for many years. NIST really is composed of or its hierarchy really is a number of laboratories, including communication technology laboratory, engineering laboratory, information technology laboratory, and others. And our team is really part of the communication technology laboratory, and we are focused on industrial wireless. And part of what NIST is doing is really offer a number of services and resources to the public, including like all these measurement services, publication software, and data, standardized like guidelines, and so on. And other programs that's also very relevant. And I would say mostly, I would say 100%, but mostly all these are free for public to use, I would say, or available for public to use. Okay, so what I would say, what our team is doing is really our mission, I would say, to enhance the implementation and deployment of industrial wireless systems and operational applications by focusing on improving reliability and latency and resilience of these systems. And in order to do so, we have really, I would say, this is a general like process in what we are doing in our lab, and also like here's I would say a subset of our collaborators while we are doing our work. So we have a large number of collaborations with industry in order to make sure that the work that we are doing in our lab is really very relevant and very practical, which include, like, you can see the list include Boeing, Intel, Google, Yokohama, and others. So what we do in our lab really is, again, like in order to be practical, we very focused on getting field data for different aspects. Like we do like spectrum measurements, like where we measure the spectrum in different operational scenarios to see like again, like what's happening in the spectrum, who's transmitting, how they can the networks coexist, and so on. We also do channel measurements, like in order to understand the physical channel in industrial scenarios, and like we use this data to do like use case identification and share it with the public. Like so, we do a lot of measurements. Our second part is really using these measurements to create models. We have been like doing this for the last few years, like creating channel models, channel characteristics, creating like I would say use case models, what's happening in different use cases and different scenarios. Operational models, even like how the wireless systems and wireless channels got like practically coexist or practically impacts like the use case of the operational use case, like and we do all this like either in the field or using the test beds that we build in our lab. So we build test beds to correct real measurements, and usually these test beds have real wireless equipment connected to them to measure the performance and to test different scenarios. And finally, we produce different sorts of guidance, including either guideline documents or standards or papers, like journal and conference papers. And I would say our most recent work is really the standard that we are working on right now is the IEEE 3388. This is like some of our contributions. Like we produced, like we are producing now a standard, but we produced already 3 guidelines documents, include the guide to industrial wireless deployments, and then like wireless user requirements, and one was a specific use case, like I would say guidelines for the Navy shipyard. Now we're working with the IEEE P3388, and we have multiple collaborations, either through discussions or real collaborations, like what we call it at NIST, like creative, like which is direct research collaborations that we had with Intel, Yokogawa, Cisco, and Ecolana, and I would say now FileServe and others. And we usually like produce conference journal papers where we attend like most of the, or we're trying to attend most of the big conference in industrial wireless just to have the discussion going, like similar to what we have today. Hopefully, I would say I hope I was there in person, but it was very hard to attend. But so this is like I would say a snapshot on what we have in our lab. I'm not gonna talk in very detailed about this. So we have, as I said, like test beds, like you can see robot arms in here, and they are communicating wirelessly. We have a 5G test bed, like we have real 5G equipment, which again connected to these robot arms. These robot arms are really connected with multiple protocols, like they are connected now with 5G, Wi-Fi, using time-sensitive networking in our cooperation with Intel. So practically, we try to build like these use cases, like these robots really doing multiple things. Like some of them are really this leader follower scenario. We are using them also for a teleportation use case. So we use them in multiple scenarios to test multiple, I would say, wireless technologies and multiple deployment scenarios as well. And in order to replicate these scenarios themselves in our lab, I would say we have multiple measurement and radio environment control. So we have like a couple of chamber in our lab. We have a channel emulator. We have a mesh attenuator. This is really a more like detailed list of the equipment that we have in our lab for the like channel recreation and measurements. One very important part really and what we are doing is to be able to measure the performance accurately, so that we can really correlate what is happening on the wireless domain to what's happening in the operational domain. So this is like, and of course to reflect this in to the standards work. So I will at least finish this introductory part with a quick slide about what we are doing in the IEEE 3388, where we really try to, in collaboration with many of the working group members, on putting together a standard process for evaluating industrial wireless system performance. And was really interesting that we found out for these time-critical systems or industrial wireless systems, there is no specific standard in how they perform. Like mostly, like system integrators, when they put them together, they follow their own process, which is usually successful. But it was a good way to do things is to do this standard process, how to evaluate performance, what metrics to measure, what scenarios to put this equipment in, and so on. So the standard really provides a standard test framework, and then building profiles for specific scenarios, like different industries, different environments, different like types of interference, like either electromagnetic interference or environments. The standard is really technology and band agnostic, like the framework that is offered now in the standard, again, still in process. So I would say it's in piloting now, so hopefully it will be approved soon and will be available for everyone. But it's technology and band agnostic, and try to focus on the mission critical low latency applications, provide what are the measurements for propagation interference that should be done for such systems. So that's, I would say, that's a general day on about what we are doing. There is, of course, a lot of details happening, but just let you know what we are doing, at least from the research perspective. And thank you.
Thank you. All right, so Next, we're going to move on to Dave. Hey, good morning, Dave. Yeah, Dave is a principal engineer and researcher at Intel Labs, and he also serves as a president for Avenue Alliance, which is an industry-wide alliance looking at, kind of industrial networking problems across Wi-Fi, 5G, and related settings. Yeah, Dave, please.
Great, thank you, Hongwei. And can you hear me well and see my screen?
Yes, we can see you, hear you, and see your slide.
All right, great. And thanks again for the invitation. And unfortunately, I couldn't be there in person, but hopefully next time we'll be able to visit our state. I just want to take this time to say a few words about what we are doing at Intel to enable real-time and mission-critical systems, including wireless as well. So just be brief, and we can have a discussion during the panel. So Hongwei, you mentioned about the really hard problem of enabling mission-critical wireless that you can bet your life on, right? I think that's really a very hard challenge. But one thing that at Intel we are looking at this problem is from the perspective of a converged network. We will enable these applications and these real-time or mission-critical systems in the same network that you can share with any other application. So we don't want to have to build dedicated network only for a single application. So this is one of our main goals, what I call converged networks. And this has been around for a while, just trying to promote this broader application in different markets. You can see from industrial, professional, audio, video, automotive. So many markets can benefit from this convergence of networks and computing as well. One example where this is happening as we speak is in the industrial market. In the past and still today, many deployments are based on dedicated networks for real-time systems. And we're trying to work across the industry to move these networks to a more standard-based networks using off-the-shelf connectivity solutions like Ethernet, Wi-Fi, or 5G, and sharing also general-purpose computing infrastructure, right? So this is one of the examples where this transformation is happening. A key performance aspect of these systems, right, is time and being able to execute and coordinate actions with the precise synchronization. This is very important for many mission-critical systems. And also being able to guarantee delivery of data, execution of tasks within deadlines. So time synchronization and timeliness are two of the most important performance metrics that we're looking at, when we talk about these real-time systems. And in terms of the technology development, some of the areas that we've been focused on are what we call time-coordinated computing and connectivity, where we're trying to provide tools and capabilities within the hardware to synchronize and to execute tasks with the time it needs, right? So that's the part we call time-coordinated computing within the system, but also enable tools that you can guarantee data delivery with determinism across a network, a distributed system. And that's where you can have wired or wireless connectivity. But no matter what you use, how can you ensure data is delivered within strict bounded latency and with high reliability? So those are some of the areas we've been working on. And the idea in the end is to have a shared infrastructure that includes wired, wireless links and can share, different applications can share, and including also the edge computing infrastructure. We are working on these problems across the industry and academia and the governmental entities. Mohammed, for example, is one of our collaborators as well in NIST. And the idea is actually we build on standards-based solutions. And one of the examples I want to share is the work we are doing in a combination with IEEE 802.1, the time-sensitive networking group, IEEE Wi-Fi 802.11, 5G, Ethernet standards, and the Avenue Alliance, which is an organization that develops testing plans and tools and programs for certifying conformance with some of those IEEE standards. So the idea is in the end that we can develop standards, we can test them, and we can ensure devices that go to market, they can serve different domains by implementing these standard real-time capabilities, so TSN capabilities in an interoperable way. So this is one of the industry areas that we've been working with many other partners. And just to conclude, I want to talk about some of the research challenges, right? As I mentioned earlier, guaranteeing time synchronization between devices within a large-scale distributed system, especially if you're going to deploy this in a wide area like industrial or even rural areas. Guaranteeing latency are very hard challenges, but there are other problems. After you, even when you can meet time synchronization or latency deadlines, there are other problems that you need to address as well, which are related to how you configure those systems, how you make them to operate smoothly, even when you have mobility or issues with wireless communications, which are typical. And also how you automate the process of optimizing these systems using AI and other tools that are available. So a lot of hard problems to solve in this domain, and there's also very interesting areas for research. So with that, I'll be happy to discuss further in the panel, and thanks again for the opportunity.
All right, thanks, Dave. So next we're going to have Ben Han from Collins Aerospace. My closest neighbor here in Iowa. Ben has been, he's a director at the Collins Aerospace Research Center, and his own research has been actually about far edge network, tactile networks and so on. He's also our liaison between the Collins and ISU. Thank you, Jim.
Good morning, everybody. So, as Hongwei said, I work for Collins Aerospace. I've been working there for about 18 years. My undergraduate research was on distributed sensor networks and how you can use machine learning to reduce the amount of data that you send between those networks and how you can maintain mesh networks of them. This got me my job at Collins. At Collins, our research areas currently focus on low size, weight, and power equipment for doing directional comms networks. Really, how do we bring the cost of those things down? Typically, military systems are highly exquisite. How can we use lower cost 5G components and things to bring that cost down? Also looking at 5G and future G at the tactical edge. So just a little bit about Collins for those of you who don't know it. Collins Aerospace used to be but still located in Cedar Rapids, but used to be headquartered in Cedar Rapids. We're now 1/3 of Raytheon, Collins Aerospace, Raytheon, and Pratt & Whitney. So we have a much larger footprint. We work largely on commercial aircraft connectivity, glass cockpits, avionics systems, and on the military side, military communications. So you might ask, why does a commercial aircraft and military communications company care about ARA wireless and open standards? And well, the reason we care is because the overlap between these areas is immense. On the commercial side, we're looking at things like the connectivity of commercial aircraft in as they're flying across the country, collecting health statistics, getting data as they land and pull into the airport. How do we swap out movies, cabin entertainment systems? How do we get health statistics? How do we do all of that quick and get turnaround? How can we use these wireless infrastructures at the airport for helping get people checked through faster? How do you scale at an airport when you have so many people that are there and you have a hard time with the connectivity? We also care about how these systems interfere with things like commercial radar. So as the aircraft are landing and they're coming in, how does that interfere with new modern wireless systems? And the ARA lab and this place being in our backyard helps us test those kinds of things. On the military side, the use case is not identical, but very, very similar to the rural wireless use case. Essentially, you have no infrastructure, limited connectivity, bad line of sight, bad terrain. You want to do everything from get data from low-cost sensors all the way to real-time command and control of autonomous UAVs, pulling video down. And how do you do that without infrastructure? So being able to look at the technologies that 5G and future wireless and things bring to that and how we can leverage those. On the hardware side for the military, we're really looking at, like I said before, the how we can leverage like commercial ESAs at scale. How can we take those electronically scanned arrays and use those for military waveforms? How can we take all of the system-on-chip work that's being done by folks like Intel and others across the board, and how can we take that and leverage that to make lower-cost radio systems? And then on the software and waveform side, how can we leverage the great work that's being done in 5G mesh networking, side link capability, integrating all of that scalability capabilities into military networking, which typically doesn't have that today. With Hong Wei's team, we're currently looking at how we can take things like MP Quick, which is a congestion and aggregation, link aggregation set of protocols, and we can bring those to military mesh networking. And then in the future here, we're going to be looking at NTN, non-terrestrial connectivity, and how we can bring that into military comms in a low-cost way. So those are the areas where we're doing the research and sort of those touch points, and why this is a big deal for a company like us.
Not least, we have Professor Song Han with us. He has been actually spending many, many years studying real-time wireless systems. Please welcome Song.
Good morning, everyone. It's my great pleasure to be here, to be part of the panel. As Hong mentioned, I have been working on this field for quite some years. So today I wanted to take a couple minutes, to describe the work that we have been done and what we are working on. Hopefully that can serve as a basis for the panel's discussion. So today I mainly talk about my work on industry IoT systems, mainly focus on the protocol design and resource management. So I think as the other panelists have mentioned that we can see the critical difference between the industry IoT systems and the commercial IoT systems. So there are some unique characteristics of those industry IoT systems for mission critical applications. So for example, they have the stringent performance guarantees regarding timing constraints. They have the certifiable reliabilities and the robustness, especially in the presence of unpredictable environment. And typically this kind of industry IoT systems, it's heterogeneous. There are many different heterogeneous components together, and they are deployed in large scale in a distributed fashion, So, so my group, my group is our work on the industry IoT system mainly focus on 4 different areas. First one is we work on the industry wireless protocol design for different industry applications, because we have different industries, they have different requirements for the wireless communication infrastructure. And the second area is focused on, once we have this kind of real-time wireless modules, how we are able to group them together into the real-time wireless networks, and how to manage those kind of resources to meet those requirements regarding timing, reliability, security, all the stuff. The third area, we also build the security communication framework for the industrial IoT systems, because this kind of system are deployed for mission-critical systems. Security, privacy are all very important things, especially considering those kind of resource-constrained platforms. We are also building systems and testbeds. Okay, of course, it's not as comprehensive as Hongwei's Ara systems. Okay, but we are building different systems for different wireless communication protocols, and we are integrating them together into a heterogeneous platform. And hopefully, one day it can be serving as a community-based testbed. We can serve the broad community. Sorry. So this is more like a research roadmap. Okay. In my lab, okay, so you can see that, okay, our work is more like organized in this kind of a layer structure. From the very bottom, we are working on different wireless communication protocols, and we have the dream that hopefully, okay, one day we are able to unify all these protocols together using the same hardware, but we can softwarely program into different protocols we can deploy in the field, so that in this case, we can reduce the hardware cost, okay, in the future development. And as David said, okay, the TSN is very popular. It's coming up, okay, and we are using, currently we have built the TSN testbed at UConn. We are using the TSN testbed to interconnect all these different wireless communication protocols to form these heterogeneous, large-scale industry IoT systems. And building on top of it, we design different resource management algorithms and framework, okay, to manage those kind of resources at edge, resource management at the TSN network, and also the resource across this kind of hybrid network, because it's a heterogeneous network. It's not a single A, just the resource management for a single network. And then we build on different applications on top of it. We take this kind of solutions and the hardware or software as our weapon, okay, to tackle different practical problems. You see that we applied our solutions into different domains, process management, smart manufacturing, power systems, smart health, the structure monitoring system, and also we are working with NASA, okay, for these aerospace applications. We haven't got a chance to work on agriculture-related applications, so this is the reason why we're here. We want to understand the challenges and opportunities in this domain, so hopefully we can have some future collaborations that we can contribute to this community. I will not have time to go through all the details regarding those wireless systems we developed, but I just wanted to share the storyline, okay, why we want to design these different heterogeneous real-time wireless systems. We started from the wireless heart, okay, many of you know this. This is the first international real-time wireless communication protocols for process control. So basically, it's quite successful, okay, nowadays, okay, they have like $1 billion revenues, okay, for the process control industry. And then we move from wireless heart, okay, working with the Texas Instruments, okay, on the 6-stage protocol. So this is basically, we are trying to move from this OT technologies to this Internet of Things technology. We have this seamless integration with the Internet of Services, okay, to be able to support the large-scale deployment. We try to apply this kind of technology into different domains, but we failed, okay? Because we see that, okay, there are different industry applications, especially for some high-speed control applications. This kind of a low-speed wireless real-time wireless solutions cannot serve the purpose. So this is the reason we work on the real-time Wi-Fi or some similar flavor of those kind of wireless TSN network. We are trying to perform the deterministic performance, okay, at the bottom layer. Okay, so in this case, we can support mechanical control, robotic control, and we developed those solutions on both commercial off-the-shelf devices and also built on the software-defined radio solutions. On the other very extreme, okay, we work on we call it wireless-powered communication network. So this is basically that we assume, okay, in the future, okay, we have a pervasive deployment of the sensor devices in the warehouse, and they are batteryless, okay, and but we still want to maintain those real-time monitoring of the warehouse, okay. So basically, what we designed is like using the wireless, okay, to power those different devices, okay, and we are using those fixed base stations and also those moving robotics devices, okay, to be able to moving around this field, okay, to charge different devices. So to maintain this kind of sustainable real-time wireless infrastructures, but without those kind of overhead, okay, to do all those kind of replacement, okay, recharging of those kind of powers, okay, batteries, okay, on the device. We are also recently, okay, looking into 5G system. We are new in this area, we are still learning, but we are working on different aspects, okay, to try to ensure those kind of real-time communications for the 5G systems. We focus on the radio access network. We designed algorithm for real-time downlink flow scheduling. We designed the real-time uplink flow scheduling based on the configured grand scheduling, try to minimize those kind of overhead as much as possible. And also we work on the coexistence between the eMBB traffic and the URLC traffic, okay, to try to guarantee those kind of performance for the URLC traffic. This is basically the testbed that we are working on. So we are having the TSN testbed. We have this different heterogeneous wireless, real-time wireless edge networks. We are integrating them together and trying to be able to serve different applications. Okay. Lastly, okay, we are also working on quite a lot of different research, okay, on the resource management, how to manage those resources. So our work can be typically put into 4 different areas. Okay, one is focused on how to do the real-time flow routing, scheduling, analysis. It's more like offline scheduling to guarantee that, okay, with the kind of a schedule, we are able to satisfy those timing reliability requirements of those applications. And as several other panelists mentioned, so this kind of a reconfiguration is also important because we are in the presence of many different internal, external disturbances. So we work on dynamic network resource management, how to rapidly adapt to those kind of disturbances, but still I wanted to maintain those real-time and reliable communication in the systems. And another work that we're working on is partition-based resource management. This is basically based on the observation that, okay, nowadays we are using the same infrastructure to support many different mission-critical application systems. They are coexisting, just as Dave mentioned, it's more like a convergent network, right? So how we are able to perform the resource partitioning for different applications coexisting on the same network, but still want to maintain those kind of timing and reliability performance, right? So basically, we are based on those kind of real-time resource partitioning techniques, okay, to be able to support those coexistence of different applications. Finally, we're taking those computing resources into consideration because we are not only dealing with networking resources, we are talking about the end-to-end latencies, including also networking resources, computing resources, maybe across different layers. So in this case, we propose this kind of a composite resource management solutions to be able to take both the computing resources, networking resources into consideration and try to guarantee those kind of end-to-end latencies, including different heterogeneous resources into consideration. With that being said, okay, I wanted to stop here, okay, but I wanted to thank all my collaborators, students, okay, I'm just a very small part of this whole team working on these different works, especially thanks to all the funding agencies, because I have my program director sitting here, so definitely I wanted to thank all the funding agencies to support our research. Thanks a lot.
Okay, great. We have mics on the floor. I guess as you start thinking about the space, please feel free to share your questions with the panel. So just to kick things off, let me probably a general question for you all, for all the panelists here. Actually, one thing yesterday I was sharing one slide showing how Profinet, right, one of the leading industrial wireline solutions was designed. I had another slide that I didn't have time to show. That's about how airplane, like the kind of network, control networks that's there on the airplane, the level of redundancy, the dedicated design there. So, but of course, many of those are not feasible, right, in the wireless world. I guess from your individual vantage point, from different industries or government, different organizations, what would be, let's say if we get to pick top 3 things to work on to encourage the community to work on, what would be the top 3 things that you would pick that if, we get to have a fantastic job that's going to have a transformative impact on both the science, but also actually the practice of mission-critical wireless networks, whether that's in factories or in airplanes or defense?
So I would say big research areas would be, one is reliability. That's key to us, particularly when you're talking about aircraft networks. It can't ever go down. That's equally critical in a military space too, when folks' lives are on the line, making sure that you've got redundancy in your data links, multiple paths back through your networks. And while you're doing that, controlling the latency. How do you, in a mesh network or in any kind of wireless network, as things are moving around and topologies are changing, how do you ensure that not only that you've got good latency and connectivity, but that doesn't change as things move around? In an aircraft, this is absolutely critical to the point of being a requirement. You don't fly unless you can, formal methods prove that this is a thing that is always going to be like this and you're going to get that latency. And in a military space, it just becomes practical as your networks get wider and wider and things get further and further apart, making sure that you can manage and maintain everything. So I would say those are some of the major research areas that we're looking at, is essentially the reliability and latency maintenance as networks scale and become more complicated and you mix multiple links and of the likes.
Thank
you. Hello? Yeah, I fully agree. Okay, as we mentioned, timing is critical, reliability is also critical. So I think, to me, I think the very important aspect is basically to understand the channel, because we are trying to ensure those kind of real-time communications. So we definitely need to understand the environment. We deploy those kind of real-time solutions into the mission-critical system, especially for the mission-critical systems. So there are many different ways, to do so, right? For example, in the some industries, they do the very careful site survey, very controlled environment, to ensure that, they understand the environment. But certainly it's not enough, because we know that, as Hongwei yesterday mentioned, right, the weather changes, big rains, they are certainly will change those kind of channel conditions. And also in the indoor environment, certainly nowadays, those factories are becoming more and more complex. So they have quite a different indoor structures, and also they have a lot of moving vehicles nowadays. They have more and more those kind of deployed UAVs, ground vehicles. That will actually create a lot of challenges, right, to understand the channel, because when we are working on those kind of real-time wireless network design, we want to make sure that we have the deterministic performance. So basically, those unexpected interferences certainly is the enemy for our system design. So I think that, to me, this is the one of the most critical research. I think Mohammed just mentioned that working group. I think that's a wonderful, wonderful working group. I was also part of it. So that is basically for those kind of performance measurements, channel modeling, interface modeling, for those industry environment. So I think the second one, to me, is more like it's a balance. So on one side is the increasing demand of those real-time systems. Now, I mean, if we take a look at those evolution of the real-time wireless from the very low speed, to the middle speed, to the high speed. So this is also obviously driven by the application, right? But on the other side, as we say, those kind of environments that we deploy such systems is becoming more and more complex. Not only we have more devices, we have those kind of mobility issues, but also people are not anymore using those kind of dedicated infrastructure to support those kind of systems. 10 years ago, 15 years ago, they have a dedicated infrastructure for this particular mission-critical systems. But people now say, we don't want to do this, We want to be able to leverage the infrastructure, but we deploy many, many different critical systems on the same infrastructure, or we have those different mixed critical systems. We have some mission-critical applications with stringent deadlines there as well, but we still have some other best effort traffic there. So how we are able to handle those kind of coexistence of this these different time-sensitive systems, and satisfy the requirements. To me, this will be the second very important research questions. Yeah.
Okay, great. Dave, Mohammed, any comments from your side? Oh, yeah. Yeah.
Sure. Thanks for the questions. And can you still hear me?
Yes, yes.
Okay, great. Yeah, I just wanted to add, right? I think those points were great already, but one way we look at these problems, we see there is a lot of evolution in the wireless protocol design, or the wireless connectivity design. Wi-Fi, 5G, they're all evolving, adding more features, right, to address reliability concerns and latency. But one additional area that could get more attention, I believe, is more the co-design of the applications with the network, right? So I think still we design these networks and we try to, even like when we look at 5G, we try to provide ultra reliable low latency, but without really, when you deploy them, there is not really a lot of context coming up from the applications to really help the network identify what data is really critical at what time, right? If you have to reserve resources for a certain application all the time, then it becomes inefficient. So I would say more cross-layer information sharing between the application down to the network, so that you can really understand what's time critical in the same network that there are, best effort traffic, right? I think that's one of the interesting areas. Of course, others related to how you actually manage these complex systems and look at the system level, building test beds. I think this is something, your group is probably doing at Iowa State as well. And, I think that continues to be important.
Mm-hmm. Yeah, yes. Thanks, Dave. Mohammed, any?
So, yeah, I would say I will just add, like, practically maybe not really adding, but just complementing what has been said. Like, I think one important aspect really is having data. Like, a lot of things nowadays really need a lot of data to understand what's happening. So either from Professor Hung said, like, about the understanding the channel, or what they've said about understanding, like, or the code design, really, in order to understand both, like, the channel or the operational system itself and how they interact, that means a lot of data. So practically, whenever we can get data, that's really very beneficial to be able to, I would say, apply wireless in different scenarios. And of course, nowadays, like, I would say most of these data could be used with AI modeling tools. Like, I would say, for all these complex applications, that's something we are trying to do. I would say it's still in a small scale, but I would say modeling tools now are really pretty much improved using AI tools. So modeling a lot of these systems and wireless channels using AI tools will be very beneficial in achieving these requirements for this time-critical system. And the last thing really is to understand the practical requirements. A lot of standards nowadays have this very, I would say, theoretical requirements on how, like, either for reliability, latency, scalability, like how to achieve or what to achieve really in order for these systems to be operational. I would say what we found in many cases, like, every system has its own requirements, like to operate well in a satisfactory manner. So understanding these practical requirements for different systems is really also a very important aspect when we are talking about deploying in these advanced systems, I would say.
Yeah, I see. Yeah, thanks, Mohammed.
Yeah, good morning. I have a question about the real-time network and talking about timing guarantees. Are those deterministic in nature? Are those probabilistic in nature? And what kind of environmental properties must be held for either deterministic or probabilistic guarantee? In particular, the Ara network that we have here, is that capable of offering any kind of timing properties?
So I would say, this is just my opinion, maybe, and I think it goes back to what one of the folks said about integrating the apps with the networks themselves. If you let absolutely anything on the network do whatever it wants, and you have whatever applications running, and you have a complex environment, I would argue something like that's going to be very non-deterministic and very hard to track down. However, if you can get good channel characteristics and you can start learning what that channel is and it doesn't change dramatically, if you know something about the humidity and the distances that you've got and things aren't changing, then I think there is some probabilism that you can bring into that. And then when you can control the applications as well and understand who's going to be sending what data when, you can start to start to get something that's more manageable and something that I think you could apply more formal methods type styles to try and predict and make certain guarantees about the network. Otherwise, I think it would be very hard in these types of networks, particularly as things move around and the environments become unknown.
Yeah, thanks for the great question. So I think the question depends on what kind of mission critical system we are talking about. Okay, so for some of the systems, okay, they do want to have we call hard real-time systems. So which means we cannot afford any package job, okay, or missing those kind of deadlines. So we call this kind of system to be hard real-time networks. So which means we put the highest priority, okay, for those kind of applications, those kind of flows, okay, for this kind of mission critical applications. And we are by all means, okay, trying to allocate the resources, okay, apply different diversities, okay, to be able to support those kind of communications. So for example, there are many different ways, okay, to achieve this or try to approach to this kind of hard real-time systems. For example, they can apply the different channels. They can apply for like the redundancies, okay, on the per frame level or inter-frame level, okay. So basically, you can provide redundancies into the frame, okay. You can basically apply different type of retransmission mechanisms for different packets, okay, to be able to significantly enhance this reliabilities and timing constraints. But of course, I mean, again, all those kind of retransmissions or those kind of redundancies has to be all satisfied, okay, by the deadline, okay, that we put in this kind of a hard real-time systems. On the other hand, okay, many of those kind of we still call like a mission critical systems, but they can tolerate some of those kind of packet loss. So, so which means that we typically we call them like a probabilistic real-time systems, or we call the soft real-time systems. So in this case, we have some flexibility. So which means we are we are able to tolerate some of them, but still we wanted to have some like theoretical model to support it. It's not like simply we just drop some packets, because in many of those control systems, if you drop randomly some of those control signals, that's okay for the controller design. But if you have a burst of the drop of the control messages, that's a disaster. So in this case, we have to design different the scheduling algorithms, okay, based on different model, like the KM model, right? So in this case, we are able to have some flexibility, but still we wanted to be able to probabilistic fashion, okay, wanted to be able to meet those requirements. So again, it totally depends on the natures of those mission critical systems, because the definition of mission critical system is still like a weak, because many people can claim, okay, in different industries, they have a mission critical systems. This is just my opinion.
Yeah, thank you. I guess the network itself has to have some deterministic characteristics for it to offer any kind of deterministic guarantee, right? So it's a chicken and egg kind of problem, and right. So and the wireless network, by definition, as opposed to wired network, would have some stochastic characteristics to built in.
Yeah, I would think so.
Yeah, definitely. So typically, to the best of my knowledge, okay, many of those real-time wireless solutions, especially designed for the mission-critical systems, you have to, based on some fashion of those kind of TDMA systems, so which means that you divide the time into different time slots. Of course, I mean, the time slot could be varied size, okay, depends on different rate we are using. So in this case, you can generating those kind of schedules, okay, in a deterministic fashion, okay. Of course, taking those reliability into consideration, you can generate the kind of schedules. This is not only for wireless, but also for the wired. For example, for the TSN network that Dave mentioned. So it's also like you have a time synchronization, very high precision time synchronization. Okay, you have TDM-based systems. You can, for example, you have the TAS, like time-aware shipper-based schedulers, right, to be able to control those kind of gates at a different switch, decide, okay, at what time, okay, which frame or which flows will be go through, right? So in this case, globally, you can construct this kind of deterministic schedule, right? But of course, I mean, this kind of system, it's in the presence of many different disturbances. So which means it's not like we deploy the schedule, it works forever and never, okay? Maybe it works like 20 years ago for those kind of very dedicated, controlled systems. But nowadays, also as Dave mentioned, we need to have those reconfiguration in the runtime. But how to perform those reconfiguration, trying to minimize those kind of changes as minimum as possible, because you don't want to basically propagate this kind of change to the whole system. You want to be able to minimize this kind of change, but still you want to meet those kind of requirements. That's the challenge, okay, in my opinion. Yeah.
Thank you.
Dave, Mohammed?
Yeah. I just wanted to add one point. I think as was said, right? First of all, I think we call this system deterministic, but I guess strictly speaking, we're just trying to increase the probability that you can meet a certain latency deadline, right? So it's not 100% all the time. Of course, when you're talking about wired systems, because the disturbances are less, you can reach very high reliability or very high probabilities, right? Now, wireless systems is harder, right? Given, like you said, the stochastic nature of the wireless channel. But what we are seeing is, and I'll give the example of Wi-Fi. There are new tools now that are adding more capabilities to apply some of these scheduling capabilities or resource allocation capabilities that are making it more deterministic compared to 20 years ago when Wi-Fi introduced probabilistic QoS, right, with channel access, random channel access with different channel access parameters for different queues. So that was really probabilistic QoS. Now there are new tools that are adding more capabilities to actually reserve resources, provided that you can control what the applications do, right? So that's the other part, as was mentioned earlier. You can't guarantee determinism if you don't control the application. If you can't say, okay, I want determinism to send anytime, any data, that's not realistic, right? You need to have some kind of policy and shaping of the applications too.
Right.
A quick addition, really. So I think almost everything has been said. So I think the whole idea of randomness versus determinism is really how this randomness really, as like I would say, the question is saying, like, the practical, there's always randomness in the wireless part, on the wireless medium, but really I would say it's how it propagates through the different layers till it reaches to the application layer. So I think the whole thing, and when we are talking about a communication system for time-critical application, like I would say, how to stop this propagation of randomness through the different layers. So I would say, I see it's like very similar to uncertainty analysis, really, to increase this determinism or to increase the confidence. I would say it's really how to stop this propagation of randomness, and that could be done in any layer in between, but the earlier it has been done, the better. So that's why when we do things closer to the wireless medium, to the place where there is most of the randomness, I would say, of the wireless system, that will practically limit or increase the confidence on how we achieve this determinism on the system. And of course, it will really very much depend on the application, I would say.
Okay, great.
Thank you.
Oh, yeah. Any other? Yeah, please.
Do you have a question? No more. Okay.
Okay. Yeah, maybe actually a follow-up question on this. I think relates to what Dave mentioned, and this co-design, right? So, so what's the state of art and practice in terms of, how to think about the design itself, like co-design? Like, for example, how do you model the even wireless network in certain ways that's generic enough to hopefully a diverse set of applications, right? And where are we in terms of being able to provide high fidelity models that can be used by application in this co-design, Any comment?
So I'll say it's two dramatically different spaces for us. On the aircraft side, I would say the process for co-design is a multi-year process where you start at the base requirements and they're going all the way up to these, on these wired networks, these applications will only transmit these packets at these times. They're tightly scheduled. Everything across the entire aircraft, whenever you're trying to do those reliable systems, is designed to the nth degree, and it's less of a scientific process and more a pure engineering process of laying all of that out and meeting those guarantees. On the military side, I would say it's still sort of the Wild West, because they have the applications that they want to use, they have the way that they've done warfare going forward. And now it's how do you bring these new systems in and take the existing applications and things that they've got and apply it. So there's some of that co-design going on as we move away from legacy military message sets and getting into IP and how do you allow a bunch of users to use those networks. But not as much as there should be at this point, I would say. So that's sort of the two sides of regarding the nitty-gritty of the design. That's not particularly my area. I think one of these folks here have some more information on that.
I think different people have a different definition for the co-design. Because in my experience, okay, when we say co-design, we are talking about basically we are design different layers together. So for example, for those real-time wireless system design, okay, typically, I mean, certainly we can see that I work on MAC layer design, okay, to ensure those kind of deterministic communications. But however, okay, now if we can have the co-design between the physical layer and also the MAC layer, okay, that certainly can be able to further optimize the performance of the systems. I mean, actually, I'm working with my one of colleague, okay, it's focused on the communications, right? So we are basically trying to move our real-time wireless systems, as I briefly mentioned in my presentation, try to basically building those kind of software to radio platform, okay, so that we are trying to, it's our dream, okay? We don't know how long it can be realized, okay, but we hope that we can have like a one hardware platform, okay, but it can support many different those kind of industry wireless protocols. So in this case, because nowadays, okay, one of the pinpoint from the industry, to the best of my knowledge, is that it's they have a lot of technologies, right? So they have, if you go to like some process automation or manufacturing application, you see that they are not basically just using one networking technology. They are using many different wireless technologies. And also we know that, okay, those kind of technologies, they are evolving, okay? 5 years ago, okay, they are using technology A, now technology B is emerging, okay, 5 years ago, another technology is emerging. So that will be the very important decision for those operators and the company to decide, okay, which technology we are going to go with, okay, how we are dealing with those kind of previous investment on those kind of infrastructure. So typically they are using those kind of integration among these different technologies together, right, have this kind of heterogeneous systems, but how to manage those kind of system, it's a headache because you have to have the knowledge of all the different systems and the integration of the different systems. You may have different kind of industry gateways, okay, for this kind of protocol conversions. That's extremely difficult to maintain, sustain. So this is the reason why, okay, we are trying to have this type of same hardware, okay, deployed in the field, okay, but programmed into different software solutions, okay, serving different subsystems. So hopefully in this way, we are able to lower down those kind of maintenance overhead, okay. But of course, there are many challenges there, right? We have to get a good balance between energy consumptions, different performance requirement, timing requirements, reliability requirements of these different systems. It's our dream, okay, but we are still trying to pursue it, okay. This is one thing I think for us, okay, it's one of the co-design we are working on.
Okay, yeah, you and I.
So I was thinking co-design slightly differently when I first started there. So on the military side, I will say there's a lot of co-design along with what you just said, but also at the mission side of things, looking at what mission really needs to be executed, what power control do we need, how long do these things need to last in the theater, what nodes in the network have the most data, so how do we optimize that timing schedule, how do we optimize that structure so that those nodes can transmit the data that they need, but everybody else can still use the network when they need to. Managing the latency throughout the network through that same scheduling based on how big the deployment is going to be, based on how nodes are going to move around. So I will say from an application perspective, there hasn't been a ton of co-design. Like I said, still sort of the Wild West. But as we're building new radios and looking at across the stack, you know, the MAC layer and the scheduling and the power control and, you know, who's going to be at what power, who's going to have what part of the schedule, how's all of that going to be done. There's a lot of co-design that's currently going into that side of things.
An overall system.
An overall sort of system design based on what the mission need is.
Right. Mohammed, Dave?
Yeah, so one of the ways we are looking at co-design is how the applications share information with the network, right? I think this is one of the areas that can be improved. For example, and some of these challenges are sometimes more implementation issues, but in the recent Wi-Fi 7 standards, we actually defined ways that the Wi-Fi client can actually tell the access point what are the characteristics of a traffic stream that needs real time, right? For example, the station can tell the network that I have this traffic that sends a packet, and then I need this latency deadline and with certain reliability. So you can tell that to the network, and then the network can try to use its tools to guarantee. The problem comes when the application developers are actually don't know how to use this information, right? Or even applications that are already there in the field, right? They already built. So how do you actually tell the network what you need? So sometimes the developer doesn't think about this, right? When I'm developing my robotic application or my, drone application. So that's where, thinking about this co-design and these interfaces between the layers up front in the system design can be helpful. And maybe in systems like aerospace, where you have the engineering process, right, to actually build the whole system, that may be more feasible. But the more we can enable these, for general application, the better for the network, right, to get more context and then know what is really time critical or not. So these are some of the challenges that we see.
Yeah, that's a good one.
I would like to add maybe a couple of small points really. One of them is really related to what just Dave mentioned. I think one big challenge is really what we see, that the focus of industrial wireless deployment or mission critical wireless deployment now is mostly for the existing systems. So really the whole idea of the co-design is, I would say, it's not that much of a focus for most of the existing systems, because the application's already, I would say it's already deployed even. So most people are, or most of the wireless system design, either from protocol design or from the system integration point of view, they are really trying to deploy a system to achieve the requirements of the existing application. So the co-design is not really a part of the process. So that is really a very big challenge, that it is not, I would say it's not in the scope of most of wireless systems like designs nowadays. The second point is really that I would say we are trying to help, given that we are not really part of the industry, we are more like supporting the industry, is to find the helping tools to understand the requirements of this co-design process. So how really events that happen on the wireless, I would say the wireless domain could impact the application domain. So that is very important. Like most of these tools do not exist nowadays. Like, okay, something happens, like interference, channel became very bad. What will happen in the application domain? Probably we really don't know till it happens, really. So, and that of course brings this issue of reliability, how people could use this wireless system. So having these tools available, or work on designing and what are the requirements of these tools, like for the feedback, like to understand how the wireless domain could impact the application domain, is also a very important related aspect to this co-design issue, I would say.
Mm-hmm. Right, tools and testing, yeah.
This is just as a research area that we're very interested in that is related to this. So there's in the DoD space today, real estate is limited on all of your platforms. So there's a big push for what are called multifunction apertures, where you have an aperture that can be used for comms and sensing and radar and other things. So when you're co-designing, one of the hard problems is when your application is not the only thing that controls this aperture or has control of this system. So when you say, dear aperture, I'd like to transmit to my neighbor now, I'm a comms system, and the aperture goes, well, yeah, sorry, something else is using the aperture right now. That's one thing on the transmit side, but then on the receive side, when you're sending to me and then all of a sudden I want to listen to that, and the aperture says, no, you can't listen to that. So really the study of how those functions operate together and really how those affect the properties of a real-time network system where you still need to maintain that connectivity, but you're not the only thing that shares that aperture, is a big area that we're doing research in, and that if anybody else has ideas on, we would love to know about.
Yeah, we'd love to understand the spec a little bit. Yeah, but that'll be next probably action item. Maybe any other questions from the audience? Kind of going back to the, I guess, both Dave and Song touched on this, you know, the notion of trying to have a kind of as generic as possible platform that can serve multiple purposes, right? And also as Wi-Fi, you know, just take Wi-Fi 5G as an example, or cellular as an example, right? The way the world goes seems to be that they are more and more similar to each other, right, in terms of the core technologies being used. I guess the one question there would be how, I guess those are still going to be two separate worlds, right, given the different, you know, just requirements like power and others. But what are the key challenges of designing such systems today in general, right? Because in general, if you want to try to kind of make one platform to fit multiple purposes, that makes the platform become a little bit more and more complex. Is this an issue or not necessarily an issue? Well, what are the key? What's your take? What are the challenges there? Maybe Song, we can start with you.
Yeah, I can try. Yeah, we work on quite a different those wireless technologies. But as Hongwei mentioned, that if we take a 5G and Wi-Fi as example, actually it's not only for 5G and Wi-Fi. It's for many different. I just take like real-time wireless solutions as example, right? So they always have a different camps. Okay, those camps always compete for those customer base. So they are trying to be able to cover as many applications as possible, so they can make their technology to be as popular as possible, right? So this happens in many different domains, right? So for example, in the let's say in the process control, right? So they have wireless cards, they have AO2 they have basically the sorry, sadly I forgot the other the standard. So basically, they are ISA 100.11. So basically, they are competing with each other. And if you, I mean, because I was involved in those kind of standardization effort, you will see that, okay, previously they have two different cores. Okay, they are not have a lot of overlapping. But then they take a look at each other, their functions they can support, okay, different channels they can support. Then you can see, okay, they are getting more and more overlap because they are competing for this the customer base, right? So. Just from my opinion, okay, I don't like very complex systems, especially for mission critical systems, because our goal is to achieve the mission, right? We are not trying to make this system to be very complicated, okay, a lot of functions, right, to support many individual applications. I feel that for general like consumer applications, that's okay, because you can support very diverse applications at the same time. But for the mission critical systems, we are actually sacrificing these possibilities that we are able to allocate those kind of resources to support those very critical mission oriented applications. I might be wrong, okay, but from my experience, I really want to make sure, okay, if we wanted to design those mission critical systems, certainly generalization is important, but the first goal is we want to be able to achieve those missions we want to achieve.
Be able to reason about it and have confidence, right? Yeah. Any other comments from the panel?
Yeah, one comment. I think this is a challenge that we deal with all the time. And I've been involved in several generations of Wi-Fi standards and solution design. At Intel, we build Wi-Fi chips for clients, and it's always a struggle between complexity and cost, right? And I mean, Wi-Fi and 5G as well. I mean, these are very successful technology, mainstream. I mean, everyone is using them every day. Now, when you try to support a mission-critical system, I'm sure we could build mission-critical systems if you could design a dedicated protocol with very high reliability and very low latency. I'm sure there are many ideas we can build it, but building a specific system, right? Building silicon only for those applications is not cost-effective, or it's not doesn't make sense business-wise, right? So that's why the direction we try to go is you need to leverage the mainstream solutions like Wi-Fi or 5G and add more capabilities into them to be able to serve some of the mission critical. So that's why both of these systems, they are evolving. But again, the cost complexity trade-offs makes them evolve a little bit slow, and probably slower than you would like, right? So let's say, but today I can see you can already use some of these systems like 5G and Wi-Fi for a system that needs higher reliability, maybe in the millisecond range. You cannot use it in the microsecond range yet, right? And that is going to take longer. So again, there's always a trade-off, right? But I see these systems, the wirelesses are evolving. So you'll see more capabilities being added. But, if you ask, okay, when can we do the same as a wired connection, like support 100 microsecond deadlines? I think that's still a little bit far away because it's not cost effective, I mean, of course, you can always build your dedicated wireless for that, but not with the general purpose, wireless.
Mm-hmm. Right. Yeah, that's a good point, Dave. Yeah.
I can quickly really add, I would say, our experience with practically nowadays, we have these multiple consortiums or alliances, or practically people working together. That I would say that's a very good step towards having this generic system, I would say. And additionally, the open source systems as well. So recently we are working with this again, open source 5G. As Dave mentioned, they are still very far from achieving these mission critical, I would say, level requirements, but still, having them as an open source, many, I would say, companies working together, many modules are putting into them. Hopefully that will lead to achieve this, I would say, relatively generic system or generic platforms sooner than later. But I would say the main challenge for this open source will be always the validation. When all these are working together, the integrability and validation of these systems really become an issue, which I would say it's always this trade-off. Yes, it's open source, many people are working, but then you have other challenges will appear. But I think the idea of having these multiple consortiums in the open source is really a good step towards these generic platforms, I would say.
Mm-hmm. Yeah, great. I know there are actually so many questions we can talk about. We're actually just about on time. So maybe any last words you may have as we conclude this panel?
I don't particularly have any last words other than thank you for having me. I greatly appreciate the time to talk with all of you guys. There are a lot of areas of research that we're interested in this area. So after this, if you're interested in talking with me or working with Collins or Raytheon as a whole, please reach out to us and let me know.
So.
Yeah, the theme here. Okay, thanks for having me here. Okay. And I also learned a lot of things, these 2 days, especially from the agriculture aspect. Yeah. As I mentioned, we work on several applications, right, for different industry domains, but we haven't got a chance to be able to work on the agriculture-related applications, from what we saw yesterday on those presentations, demonstrations, the field visit. I feel that, there's some opportunities, we are able to contribute, I mean, certainly working with Hongwei, working with everyone here, to be able to solve be able to improve those kind of time latencies, okay, for those mission critical systems in the agriculture applications and in general in many different applications. So I look forward for the collaboration in the future. Yeah.
Yeah, great. Yeah.
If you have any questions, please feel free to let me know. Yeah.
Mohammed?
Yeah, I just would like to thank you all for inviting me, and thank you for all the interesting topics that we discussed. So that was a pleasure being there. Hoped I would be there in person, but thank you again for having me.
Dave?
Yeah, thanks again, everyone. And we're always looking forward to hear new ideas from the academic community, right? So we're really happy to collaborate and work, across the community. So feel free to reach out. We'll be happy to discuss further. Thank you.
Yeah, thanks, Dave. Mohammed, hopefully you can join us next time. We actually went to the cornfield yesterday. It was a good trip, despite the heat. All right, thanks. Thank the panel again. So I guess we are doing a little bit better today.